In this lecture, we're going to provide an overview of energy, work, and the relationship between those two variables, and we're going to focus on mechanical energy. And so just to revisit our definition of energy, we defined energy as the ability to perform work. And once again, when we talk about work in this context, we're talking about an object that is experiencing motion. And so, in terms of mechanical energy, there are two forms that we will address in this lecture. There is potential. The first form here is potential energy, and potential energy is that type of energy that's independent of velocity and acceleration. And with respect to the example we will illustrate on slide number 11, potential energy, you can also think about it as position energy, because the position of the object in question is going to determine how much potential work can be carried out. And so this is a rather famous equation you may have seen before, but potential energy is going to be equal to the mass of the object in question times the acceleration due to gravity times the height of the object from the ground. And that will provide us a measure in Newton meters. And it's very important that we note that the Newton meter unit is the identical unit used when quantifying torque or a moment of force. But recall, a moment of force is a vector quantity. Energy is not a vector quantity, as we can quantify its magnitude, but we cannot quantify its direction. Kinetic energy, we'll discuss it in both in translational and rotational terms, but in terms of, if we think about translational energy, it is dependent on velocity, and quantitatively can be determined by taking 1/2 of the mass of the object in question times the velocity at which that object is moving squared. And once again here, we're dealing with Newton meter units. So even though we're talking about the energy of motion, kinetic, versus the energy of position, potential, we're talking about energy in both cases, so the units are identical. And to make a note here, 1 Newton meter of energy is equal to 1 joule. So to illustrate the relationship between potential energy and kinetic energy, we'll use this example of a person jumping off a platform. Now, this is not typical of the technique a high platform diver would use. This is actually somebody that was not allowed up there during the Olympic Games, but he decided to get his 15 minutes of fame. Nevertheless, when we begin to take this approach in estimating the mechanical energy involved in moving from the 10-meter platform to the surface of the water, we have to first establish, as we've done before, a frame of reference. Now we have X, Y, we have counterclockwise rotations, all indicating positive directions. In this particular case, the only part of our reference system that we'll focus on is the vertical portion of it. So we're only going to deal with vertical motion. Now, if you see this jumper is a particular horizontal distance from the platform. However, we only consider the vertical displacement of the person in terms of calculating energy. So we have a 10-meter diving platform, and so here we have units or the height in a unit that we will use. So in terms of calculating potential energy, that's the potential energy of doing work, and the motivating factor performing the work, of course, is gravity, the attraction to the much larger body, which is the Earth. And to determine how much work can be performed, we need to consider the mass of the object in question. So we'll say this person has a mass of 65 kilograms. We previously defined the equation for potential energy as mass times g times height. And by substituting the relevant values, 65 kilograms times 9.8 meters per second squared times the height, 10 meters, we have an overall ability to perform work equal to 6,370 joules, or 6,370 Newton meters. Now, does energy get lost in this process? The process, of course, referring to the movement of the jumper once he steps off the platform and makes initial contact with the surface of the water. And so to answer that question, we now have to calculate kinetic energy. And to calculate kinetic energy, we need to know the velocity at the point the jumper makes contact with the water, because once water contact is made, there is an external force that is reactionary to the movement of the person in a vertical downward direction, and that external reactionary force coming from water molecules will have an effect on that velocity. So we go back to the projectile motion lecture, and we look for one of the four equations of constant acceleration. And so we select an equation that will work for us. In other words, an equation that will yield only one unknown variable. And so in this particular case, I select this equation out of the four, because when I go through it, I find F. I look for F, which is the final velocity. I look for an initial velocity. Of course, the acceleration due to gravity is going to be a constant. The final position, subtract the initial position. And so by substituting values, we have, of course, an initial velocity instantaneously, right at the instant the jumper breaks contact with the platform, and that we assume to be 0 meters per second. Subtract the product of 2 times the acceleration due to gravity, and the difference in the height, which is taken as 10 meters. And so as we work through our solution here, we take the square root to isolate our values, and we find a final velocity of 14 meters per second at the instant the jumper makes contact with the with the water. Okay, so as we move through, we find that the kinetic energy is going to be equal to the 1/2 of the mass times the velocity at the point of contact. And we substitute our values, and we find that the kinetic energy is the same value as the potential energy at the start of the action here. And so that example illustrates the relationship between potential energy and kinetic energy, in which the final sum of the two energies equals the initial sum. So there's going to be a trade-off between potential and kinetic energy. So on this graph here, we see that potential energy is highest at the start point, or at the maximum height, as the mass, assuming mass and g does not change. And during the course of the path, as the object changes the value for height, we see that the increasing value for velocity will eventually balance the potential energy, so that the total mechanical energy at the beginning of the movement with respect to potential energy will equal that of kinetic energy at the end of the movement. So the mechanical energy sum will be conserved here throughout the motion. In terms of rotational types of actions and energy, we talk about something called the work energy theorem, which relates the amount of work done and relating that work done to a change in the mechanical energy of the object. And so in this case, work is going to be reflective of a change in mechanical energy. Remembering that work is force times distance, which is not a vector quantity. Now, we'll use this example of knee extension to highlight the difference between positive work and negative work. So positive work is going to be defined as a situation where the direction of force application and the distance in which the object is moving are the same. Negative work is a situation where the direction of the applied force and the distance moved by the object as a result of that force are in opposite directions. And we're going to use a knee extension example to illustrate that. So in the upper right hand corner of the slide here, you see a person performing a standard resistance strength type of exercise where they're going to perform a knee extension against external resistance. Now, in order to do this, to move from a knee flex to a knee extended position, we know that this exercise is designed to strengthen the quadriceps femoris muscle group, and that maneuver is performed by the application of the quadriceps force through the patellar tendon's attachment to the tibia. Now, in this case, as we see on the slide, moving from a flexed start position to the final position, we have the force vector, as we see here, and we have the direction of movement in the same direction as that force vector. And we refer to that as a concentric contraction. So when you think about a concentric contraction, it's one in which a muscle, tendon to tendon, is moving closer to each other. So the whole muscle length is getting shorter during a concentric contraction, and that another term for that is a positive. Positive because the application of the force causing the movement is going to go in the same direction. That is going to be contrasted with what is often referred to as a negative or an eccentric contraction. So an eccentric contraction is one defined by the full length of the muscle, tendon to tendon, moving away from each other or getting longer while that muscle is activated by the nervous system to produce force. And that's what we see in this example here. So starting from the extended position, the person's leg will move back into a flexed position, but in order to produce a controlled movement of that, the same muscle group must be activated. And the quadriceps force vector is always going to be in this direction because it is anatomically constrained to work in that direction. However, the nervous system is activating the quadriceps muscles to a level that will allow gravity to overcome the force of the quadriceps in a very controlled manner. And that's why we call it a negative, because the direction of the movement is controlled by a muscle acting in the opposite direction. And this is a slide we've seen in an earlier module in this course, and this is a research study in which a number of participants were brought into the lab, and they all performed single leg knee extension. During the course of that knee extension, what we see here, this device is an electrogoniometer that is taped to the person's leg. So when the person performs a knee extension, the electrogoniometer moves and produces a tracing, as you can see here, with respect to locating the position of the lower leg with respect to the upper leg. These devices here are electrodes that are recording the action potentials coming off the muscle fibers that are responsible for producing that force. And so in this particular study, this was a study in which participants performed one set of a fatiguing set of contractions at 50% of their one repetition maximum, and women were found to be able to perform one repetition more than the men in the study, which is consistent with other studies that have demonstrated women at the same relative force level are able to perform muscular contractions for a statistically longer period of time. But I want to focus on the this example tracing of what was sampled during this experiment. So on the bottom tracing, this is, as indicated, a tracing reflecting the voltage output of this electrogoniometer, which provides us with an indication of where the leg is during the movement. So what we see here, the person is sitting in a resting state. They're instructed to lift the weight. As they lift the weight, their leg goes through knee extension. And without a change in the voltage in the extended position, the person is holding that extended position for approximately 2 seconds. And then they lower the weight back to the start position. And so because at the very beginning, the person's moving from a flexed to a fully extended position, the direction of the movement, direction of the force vector are the same, and so that defines the fact that it is a concentric type of contraction. The insertion of the patellar tendon is moving closer to the origin of the entire muscle group, which is located on the pelvis, at least for one muscle, and along the femur for the other three. And what we see here, when we see that there is no movement, but the muscle is still active, and that's what we see in the fully extended position, that's our isometric contraction, same metric length, so there's no change in muscle length. And then what we see is that the person is allowing the weight to come back to the start position. Now, a couple of things to make note here on this slide, specifically to this third phase of the exercise, is that the longer duration, so the leg is going through the same angular displacement, full extension back to knee flexion. During the concentric, it moved from knee flexion to full extension, so the angular change was the same, except that it took longer to bring the leg back to the flexed position. And so by taking longer, the movement was slower. That means the person was generating less power. And by generating less power, that suggests that the velocity of the movement is one factor that determines power output, as we'll address a little bit later in this particular module. Now, keep in mind that the loading was the same. So, person performed the extension, held it for 2 seconds, lowered it back down. The weight on through the device was the same. Now, if we take a look at the magnitude of activation of the muscles performing this maneuver, we see the big burst of electrical activity coming from the superficial portions of the muscle. That activity has to be present because it requires muscle force to hold the leg in the fully extended position for about 2 seconds. And what we see here is a drastic reduction in the amplitude of those EMG signals, of those action potentials, despite the fact that the force applied to the leg was the same as it was during the concentric phase. So the lower EMG here suggests less muscle activation, and the metabolic profile of those muscle fibers will follow suit with respect to the magnitude of the activation. So in terms of metabolic energy, eccentric types of contractions are less energy consuming than concentric contractions. So the question here is, where does, despite the fact that the active part of force output seems to be decreasing here, despite the fact that the loading was the same, where is that extra force going to come from? It comes from the resistance to the lengthening muscle from the extended back to the flexed position. And so that resistance coming from a stretching muscle, one that is increasing length, adds to the potential to produce force eccentrically. But with the same load, what we see is a reduction in activation and a reduction in metabolic turnover. Now, moving on to how we can quantify mechanical work. Work is defined by the applied force and the distance to which an object moves. And so on this graph, we're going to put the position of some object along the x-axis. We're going to place force needed to push that object across a particular distance. And in this example, if we apply a constant force, that's going to cause an object to change position, what we see here. To calculate the work performed by this force, what we simply do is multiply the x-axis by the x-axis by the y-axis, a force times the distance moved, and geometrically that is an area calculation. Recall in the kinematics unit, to calculate velocity from position, that was a slope calculation, but this is going to be an area calculation. Now, in the situation, so we have a second example here, and this is important because we're talking about the application of many forces, which is usually not constant. And so this is an example tracing of a non-constant force that is going to cause an object to change position. Now, in order to calculate mechanical work between position 1 and position 2, so we know this object has moved, okay, because it had a first position, and it moved along into a second position. It necessitated the application of some force. It's still geometrically an area calculation, but this poses a little bit of a problem for us because we're not dealing with a simple geometric shape. So the technique used to do this is something called a definite integral. It's a mathematical approach by which that will allow us to calculate the area under some type of function or some type of curve so that we can quantify the meaning of that area. The meaning of the area in this particular case is that by multiplying force and position, we're calculating mechanical work. So when we talk about mechanical work, work is only done if a displacement occurs in the same line in which the force is acting, and we'll use the pushing of a sled in this example here. So let's take a look at the top example here. So let's say that this person is applying a force of 1200 newtons. Now, assuming that the 1200 newtons meets a threshold to cause the sled to move, that we can then calculate how much work the athlete is performing on the sled. And so in this example, we'll say the sled has moved 15 meters, and the force required to move the sled will say was held constant at 1200 newtons. So we'll go ahead and calculate the amount of work performed by the athlete on the sled. Now might be a good time to pause the video, perform this calculation yourself, restart the video, and we'll see what you come up with. Okay, so welcome back. So we use the same equation. Work is equal to force times distance. And in this particular example, we're provided with the data here that we can calculate work. So we have 1200 newtons. We have a 15 meter distance, and the total work performed is 1800 kilojoules, 18,000 joules. Okay, so let's take another situation here at the bottom, slightly different. Now what we see is we see a different type of sled. This different type of sled is such that the bar is much lower than it was in the first example. So the force coming from the athlete is not perfectly directed horizontally as suggested in this photo, but is coming down at a particular angle onto the handles. And we'll say this angle looks to be about 45 degrees. Now we know that in order to move that sled 15 meters, it's the horizontal component of this force vector. So before calculating the work performed by the athlete on the sled, the first step is to decompose or resolve this vector into x and y components. If we focus on the y component, of course, the y component will not produce any horizontal motion. The y component will attempt to translate the sled into the ground. But the objective is to move the sled horizontally. So what we want is that horizontal component. And that horizontal component is going to be equal to the applied force of 1200 newtons times the cosine of the angle times the distance. And so we input our resultant force of 1200 newtons. We multiply that by the cosine of the provided angle here of 45 degrees, multiply that by 15 meters, and we see a total work performed of 12.7 kilojoules. So despite the fact that the amount of force coming through the arms is the same in both situations, this situation here actually necessitated less of a force to get the sled moving. Less of a force because the horizontal component was considerably less than 1200 newtons. Okay, so we'll take another approach at this problem. And in taking another approach to this problem, we get a little bit more realistic here. So we look at the arms and we say, well, the arms aren't quite perfectly horizontal. They're forming a 19-degree angle with respect to the horizon. And it's the horizon, the horizontal force, that's of concern here, because that's what will get the sled moving. So we still have our 15-meter distance. Now, the force to get the sled moving is the same as it was in the previous example with this particular athlete here, and that force is 1200 newtons, which the athlete would only have to produce if those arms were perfectly horizontal, but they're not because of the design of the sled and the height of the athlete. And so that necessary force will now have to take into consideration of the fact that the overall force of the athlete is not going to be the same potentially as 1200 newtons. So we still work with the same equation. Work is equal to force times distance. We know that it's going to require a 1200 constant Newton force to get that sled to travel. So we're still looking at generating 18 kilojoules of energy, of work, to get the sled from one end to the other. But we know that the relationship between the horizontal component and the resultant force is going to be one that is a function of the cosine of that angle from the horizon. And so understanding that we have an x force, that's what is necessary to move it. We have the angle. What we want to calculate is how much force has to come through the arms of this athlete. So by substituting our numbers and solving, we find that the athlete must generate more than 1200 newtons in order to get the sled 15 through the 15-meter distance. They have to generate a little bit more than 1200 newtons because their trajectory of their arms is such that it's not perfectly horizontal. So in this case, the athlete is having to lose a little bit in terms of their overall force production. Not all of that force, and it's only a small amount, 69 newtons of that total force is being lost to the vertical component. Okay, so this ends our second part of our module on energy.